Hey there! We are continuing our study of derivatives by talking about extrema on an interval. Our learning objective today is to use graphs and derivatives to find local and absolute maximums and minimums of a function. The maximum and minimum values of a function are called the extreme values or extrema of a function, and the process used to find them is referred to as optimization. There will be times when we want to find the maximum and minimum for x on an entire domain, and other times just on a particular interval. In this lesson, we're going to learn how to use calculus to find extrema rather than a calculator. Relative or local extrema are y values on the graph of a function where the function changes from increasing to decreasing and vice versa. Absolute or global extrema are the highest or lowest y values on the graph of a function or on a specified domain of a function. The graph of h of x is shown below. Determine the extrema of h of x on the interval between a and f. B is the first one. That would be a local minimum. H of c would be a local maximum. H of d, that's an absolute minimum. And h of e would be the absolute maximum. You could be asked to analyze either open or closed interval functions. Be careful to check which it is before answering. For example, this graph just keeps going. So consider the graph y equals g of x shown at the right. List the relative extrema of g of x. Well, we have a relative maximum at 2, 2. We have two relative minimums, one at -3 and -8, and one at 4, 0. Considering the domain of g, what are the absolute extrema of the function? Well, what's the absolute maximum? There isn't one. The graph just keeps going. The absolute minimum would be -3, -8. Here we have the graph of f of x. We're going to list the relative extrema. We have a relative maximum at 7, 7. We have two relative minimums, one at 2, -2, and the other at 10, 2. Considering the domain of this one, what are the absolute extrema of the function? This is a closed function. So keeping that in mind, we have an absolute maximum at 7, 7, and our absolute minimum is 2, -2. Extreme values can occur at interior points or at end points of an interval. A function may have both maximum and minimum values over an interval, either a maximum or minimum, or no extrema on an interval. However, the extreme value theorem says that if f is continuous on a closed interval, then f has both a maximum value and a minimum value on the interval. When the hypothesis or if statement is not met, either continuity or the closed interval, there's no guarantee of the conclusion, the then statement. However, a maximum, minimum, or both still may exist. There's just no guarantee. Let's explore a few examples where this happens. For each of the graphs, we're going to state where the hypothesis of the extreme value theorem fails on the interval of 0 to 3. Then we can see if the function has extrema on that interval. So for A, why doesn't the theorem apply? Because it's not continuous at x equals 1. We still, though, have an absolute minimum at 0, 1/2, and an absolute maximum at 1, 4. Graph B, f of x is not continuous at x equals 1.5. We have an absolute maximum at 0, 4.5. We don't have an absolute minimum, though, because that open dot right there where the minimum would be, the graph never quite reaches it. This one, f of x doesn't exist at 0 or at 3, and we happen to have no extrema on this one. And then D, once again, f of x does not exist at 0 or at x equals 3, but we do have an absolute maximum. I misspelled that. Maximum at 1, 4, and an absolute minimum at 2, -1. Now without a graph, for each function below, explain why the extreme value theorem would or wouldn't apply on the given interval. A, we have a closed interval of -4 to 4. However, we have a problem here at 2. There's a hole there. So we could say that the extreme value theorem does not apply because f of x is not continuous at x equals 2, which is contained in the interval. Part B, e to the x minus 2 plus 1 on the closed interval -5 to 5. That one is continuous for all real numbers, so we're good to go on -5 to 5. And then part C, h of x equals x times the square root of x plus 2. Looks like we may have a problem here. Anything less than -2 is going to be a problem. And something less than -2 is in our interval. So we'd have to say that the theorem does not apply there. Back to our graph. If you'll notice, at each relative extremum, the derivative is either 0, like these guys here, or the derivative doesn't exist. These spots are called critical numbers. They are critical because something happens there. So the definition of critical numbers, let f be defined at C if C prime equals 0, or f is not differentiable at C, then it's a critical number of f. Relative extrema can only happen at a critical value on an open interval. Global extrema must occur at a critical number or an endpoint on a closed interval. We're going to use critical numbers to find extrema, and to do that, first step is to take the derivative of the function. Step 2 is to find the zeros of the derivative or where the derivative doesn't exist. Again, those are the critical numbers. Then you'll make a table for a candidates test, which I'll show you, to see the value of the function at those critical numbers. And then we'll compare all the values to find the maximum and the minimum. Example 6, we'll find the absolute extrema of the functions below on the given interval, provided that the extreme value theorem is applicable. If not, justify why it's not. A, we have f of x equals 8x to the third minus 3x squared minus 9x plus 2 on the interval from -1 to 2. This is a closed interval. That's important. Polynomials are continuous and differentiable, so we know that we're good there. So let's take the derivative and set it equal to 0. 24x squared minus 6x minus 9. Now we need to solve for x. So we'll factor out a 3 first, and then we can factor out that next guy. So we have zeros at -1/2 and 3/4. Now we make a table, and this is the candidates test. And notice I have my 0 of -1/2, my 0 of 3/4, but I also have my endpoints. Now you can use your calculator to plug in each of these critical values to the original function. So if you plug in -1, you get 0. If you plug in -0.5, you get 4.75. 3/4 gives you -3.063. And 2 gives you 36. Final step then is to compare all of my f of x or y values to see where the absolute minimum and the absolute maximum would be. So the absolute minimum is right here, -3.063, and the absolute maximum is at 236. B, we have x minus 2 sine x on the closed interval 0 to 2 pi. That's a continuous and differentiable function, so we'll take the derivative, set it equal to 0. We'll get cosine x equals 1/2. So at what angles does the cosine x equal 1/2? This is when your unit circle in your head comes in super handy. So we have the angles pi over 3 and 5 pi over 3. And we have our candidates test. So our two zeros are represented, as are our endpoints. Plug each of those in to the original function. Get 0, -0.685, 6.968, and 6.284. So it looks like our absolute minimum value is at pi over 3, and our absolute maximum value is right next to it at 5 pi over 3. Next one, sine squared x minus cosine x on 0 to 3 pi over 2. That's continuous and differentiable. So we will take the derivative and set it equal to 0. Got the chain rule on this one. Then let's factor out a sine x. And now you can see we'll have a couple different things to set equal to 0. So when sine x equals 0, what angles are those? That would be 0 and pi. And when cosine x equals -1/2, that would be at 2 pi over 3 and 4 pi over 3. So all of that, plus the endpoints, has to get into our candidates test. Thankfully, 0 is a 0 and an endpoint. Then 2 pi over 3 pi, 4 pi over 3, and our last endpoint. And then we'll plug those back into the original function. -1, 1.25, 1, 1.25 again, 1 again. Looks like our minimum is right there at 0, -1. And the maximum, we have a tie. One is at 2 pi over 3, and the other one is at 4 pi over 3. Okay, part D. F of x equals ln x squared minus 9 on the closed interval -2, 5. Well, if we're talking about a natural log here, we need to just double check this because ln doesn't exist less than 0. So let's see what happens. X squared minus 9 has to be greater than 0, which means that x squared has to be greater than 9, which means that f of x is actually undefined between -3 and 3. So our theorem doesn't even apply. So we move on. E, do we have any limitations on this one? It's a cube root, so it's okay to have negatives under a cube root. I think we're good to just go. Let's find the derivative and set it equal to 0. Now, this one's interesting because f prime of x, I can't ever get it to equal 0. There's no x's on the top. However, we do have a limitation on the bottom in that if x equals 2, the function is undefined. So that is still a critical value. So here we need our candidates test, endpoints, and it's not a 0, it's a critical point of 2. Plug those numbers into our original function. We get 1, 0, and 4. So we have an absolute minimum at 2 and an absolute maximum at 10. That's it for this lesson. Thank you for listening, and I will see you in the next one.